Welcome to episode 26 of Pulse of Physiology. I'm your host, Dr. Jim Davis, and today we'll delve into the process of excitation-contraction coupling, a critical step in skeletal muscle contraction. This process bridges the gap between the electrical signal of an action potential that was initiated by a neuron and the mechanical action of muscle contraction. In our next episode, we'll explore how cross-bridge cycling, which is the final stage of muscle contraction, occurs. For now, let's focus on how excitation-contraction coupling prepares the muscle for that action. Now, before excitation-contraction coupling begins, an action potential generated in a motor neuron reaches the axon terminal. This causes voltage-gated calcium channels to open, allowing for calcium influx. The influx of calcium triggers the release of acetylcholine into the synaptic cleft via exocytosis. Acetylcholine will then diffuse across the cleft and bind to nicotinic cholinergic receptors on the motor end plate. And if you recall from one of our earlier episodes, when we activate a nicotinic cholinergic receptor, what we're doing is we're activating an ion channel. In this case, acetylcholine binding to these nicotinic cholinergic receptors opens ligand-gated sodium channels. This allows sodium ions to enter the muscle fiber and cause a graded potential, a depolarizing graded potential. That graded potential causes voltage-gated sodium channels to open, which allows for even more sodium influx, ultimately allowing the muscle fiber to reach threshold and have an action potential. And so once we have an action potential initiated, this sets the stage for the rest of excitation-contraction coupling. And so we're going to break this down into 5 primary steps, but we're going to dive into the detail of each of these steps. So the first one is the action potential propagation. Then we have to activate the DHP receptor. This leads to calcium release, and that calcium release allows calcium to bind to troponin, which ultimately allows binding sites for myosin to be exposed. So let's jump back to that action potential propagation. Once threshold has been hit, the action potential travels along the sarcolemma and down the T-tubules. Remember, those are invaginations of the sarcolemma that penetrate deep into the muscle fiber. This ensures the electrical signal reaches the interior of the muscle cell where the contractile machinery is located. Ultimately, this will lead to activation of the DHP receptor. Remember, the depolarization goes down that T-tubule, and inside the T-tubule, there is a receptor called dihydropyridine, or DHP receptor. This is a voltage-sensitive calcium channel located in that T-tubule. When the action potential reaches there, the DHP receptor undergoes a conformational change in response to depolarization. This triggers its interaction with the ryanodine receptor on the sarcoplasmic reticulum. This leads us to calcium release. The ryanodine receptor, which is located on the sarcoplasmic reticulum, opens to release stored calcium ions into the sarcoplasm. This calcium release is amplified by a positive feedback mechanism. Initial calcium binding to the ryanodine receptor causes more calcium release to occur. Finally, next we have binding of calcium to troponin. The released calcium binds to troponin, which is that regulatory protein that's associated with actin filaments. Troponin actually consists of 3 subunits: TNC, TNI, and TNT. TNC is where troponin can bind to calcium. TNI is the part of troponin that's bound to actin, and TNT is the part of troponin that binds to tropomyosin. When calcium binds to TNC, a conformational change occurs in that troponin-tropomyosin complex, ultimately leading to exposure of the myosin binding sites. Tropomyosin, which was blocking the myosin binding sites on actin in a relaxed muscle, is moved out of the way by the troponin-tropomyosin complex when calcium binds to troponin. This exposes the myosin binding sites on actin, allowing myosin heads to attach and begin cross-bridge cycling. But since we don't want muscle contraction to go on forever, we need to terminate that contraction. And this termination occurs when calcium ions are removed from the sarcoplasm and return to the sarcoplasmic reticulum. The primary way that this happens is through calcium reuptake. On the sarcoplasmic reticulum, there is a pump called the calcium ATPase pump. This pump actively transports calcium back into the sarcoplasmic reticulum, which reduces sarcoplasmic calcium levels. Additionally, troponin and tropomyosin reset. As calcium dissociates from troponin, tropomyosin returns to its original position and blocks the myosin-binding sites on actin, which prevents further cross-bridge cycling. So let's take this and put this in clinical perspective. Understanding excitation-contraction coupling is essential for diagnosing and treating muscular and neuromuscular disorders. And there are 3 examples I just want to briefly mention, just to get you thinking. First, we have something called malignant hyperthermia. This is a genetic condition caused by mutations in the ryanodine receptor, which lead to excessive calcium release and sustained muscle contraction during anesthesia. Okay, more contractions, more ATP is broken down, more ATP being broken down, that's more heat that's released, which can lead to that hyperthermia or increased core temperature. Next, we have myasthenia gravis. This is an autoimmune disorder that reduces the number of functional acetylcholine receptors at the neuromuscular junction, ultimately impairing muscle activation. Then we've got Duchenne muscular dystrophy. This is a genetic disorder affecting dystrophin, a structural protein which compromises the integrity of the sarcolemma during contraction. Let's wrap up with 4 key takeaways. First, excitation-contraction coupling links the electrical signal of an action potential to the mechanical process of muscle contraction. Second, this process involves action potential propagation, activation of the DHP receptor, calcium release from the sarcoplasmic reticulum, and calcium binding to troponin. Third, calcium plays a central role by exposing myosin binding sites on actin, initiating cross-bridge cycling. I'll mention this again in our next video, and I'll mention this often in class, but if you don't know the answer when it comes to muscular physiology, especially when we're talking about skeletal muscle, go back to cross bridges. Cross bridges are the key, and calcium is the key for cross bridges. Termination of contraction occurs when calcium is actively pumped back into the sarcoplasmic reticulum, resetting the troponin-tropomyosin complex. And so with that, we are done with episode 26 of Pulse of Physiology. I hope this episode has provided clarity on the intricate process of excitation-contraction coupling. Join me next time for episode 27, where we'll discuss cross-bridge cycling and the mechanics of muscle contraction. Until then, keep questioning, keep exploring, and stay curious.